This is lecture 60 for Calculus 2 on some easy work examples. I've made an effort here in this audio lecture and also in the written lecture to group the types of problems that you will have to do for work into these different categories. You can go back and look at these categories. They're going to involve whether the mass is reported as a density, and that will be in the hard problems, or whether the mass is constant. Okay, and then you have to look at what units you've been given. Have you been given pounds? Have you been given kilograms? So let's say you start off and somebody gives you force right off the bat, MKS force in newtons, and the displacement is given in meters. Okay, so let's say that you need to compute the work done on an object if a force of 20 x squared newtons pushes the object 20 meters, and you need to know where you start and where you end, because it's going to matter in terms of the force. It's x squared. What would this have to do with anything? Okay, say you want to compute the work, and you've got this, you're working in a factory, or you design a factory, saying you've got a conveyor belt, and the conveyor belt goes slow at first, and then it starts moving faster and faster. Maybe it has to slow up while the milk bottles are full, and then it can go faster as you put the labels on. And you want to compute the work in a certain segment of that of the path of that conveyor belt. So there could be a reason for this. So here's the work, and this is that classical form right there. You're integrating from x1 to x2. In this case, when it's 10 meters to when it's 30 meters along. And here's the force. You know it already, 20x squared dx. Just integrate it using the power rule, and you end up with joules, which you can express as kilojoules. So you're given force, and you're given displacement, and this is how you carry out the integration. Now let's look at a similar example in British or imperial units. Say you're given force in pounds, and the object is being lifted. So the example could be, what is the work required to lift a 250-pound box from ground level to the height of 20 feet? Right. So the object is starting here. It's the same integral over displacement. It starts at 0, it's right on the ground, and goes up to 20 feet. All right. Force is 250 pounds. In this case, the force does not vary with x. It's constant, and that's okay. It just comes out from under the integral sign. Again, you use the power rule, and now you get your answer in foot-pounds, and that's the work that's done on that object, lifting it. In both of these examples, you were given force already, and you didn't have to compute anything. You simply had to integrate it appropriately. Now let's move a little bit in complexity and say the mass is specified in kilograms. So you're given kilograms. You usually aren't going to say mass. I'll just give you kilograms. You have to figure out what to do with it. And again, let's let the object be lifted. So the example is, what is the work required to lift a 250 kilogram box from ground level to height of 20 meters? Looks similar to the other problem. We're going to go from 0 to 20. Now, what we've been given is a mass in kilograms. We need instead force. So force, because this is being lifted against gravity, is mass times acceleration due to gravity. Oh, if you're on the moon, that's right, didn't read the rest of the problem, did I? Okay, so it's 250, which is kilograms, and then multiplied by the acceleration due to gravity on the moon, which you can find in the chart on the in the written lecture. There's your force. It's constant, that's fine, but you had to compute it. So force was mass times acceleration due to gravity. 405 was the answer. That comes out from under the integral sign. Use the power rule again, and your answer is in joules. Now here is the last easy example. Let's say the displacement is given to you as a function of time. You're given, let's say you're given the mass as 30 kilograms. All right, and you know how its position changes with time. In this case, it's 5t cubed plus 6, and here's a graph of that. If you just look along there, you can see that this is displacement, this is, say, its location, and this is a time axis. The x-axis, or the horizontal axis, is time. Here's its position, and you can see that it starts off not moving very much, and then it starts moving very, very fast. So there is a velocity and an acceleration associated with that. The question we have to compute here now is, what is the force that would cause this kind of displacement? So to compute that force, we'll use force as mass times acceleration. Well, what we do know is the position as a function of time. If we take its first derivative, we end up with the velocity. We take the derivative of the velocity and we get acceleration. That allows us to compute the force. Force was mass times acceleration. It was the 30 kilogram object times 30t, which was the acceleration. So here's the acceleration right here. Here was the mass of the object right here. Multiply those two together, and this is the time varying force. This is the force as it varies with time. Now we use this expression now to compute work. It's the integral from time 1 to time 2 of the function that varies with time times the velocity, and so I have to change pens here. We know the velocity right here. So substituting, we have 900t, because that is the force, multiplied by the velocity, which is 15t squared, and integrating from 0 to t if we want to know it over 10 seconds. All right? Carry out the integration, you get an answer in joules, which you can write as in megajoules if you want.